Here we have a barrette and our barrette clamp, and it's clamped to our barrette. So that's the first step of setting up our titration. We're gonna clamp our barrette. Now, we're gonna get a beaker. This is gonna act as our waste beaker. We're gonna go ahead and get our sodium hydroxide in a steamed glass flask, and we're gonna open the stopcock or twist open the stopcock of our barrette, and we're gonna rinse out with the sodium hydroxide the barrette, making sure it's all cleaned, and we're gonna want to do this a couple times. Now we're gonna get our we're gonna set our waste beaker aside, and we're gonna close the stopcock, twist it closed, and we're gonna go ahead and get that same size sodium hydroxide beaker, and we're gonna go ahead and carefully pour it into our barrette, filling our barrette, and that's gonna be what we use with our titration. Now we're going to want to look to the tip, and we're going to make sure not to overflow it when we pour it, and we're going to want to look to our tip and see if there are any air bubbles. If there are any bubbles, we're going to go ahead and take that waste beaker, and we're going to place it under, and we're going to twist open our stopcock, and pour some of the sodium hydroxide out, and then we're going to close it, and our air bubbles should be gone. So now that we have filled our barrette with our sodium hydroxide, we're going to get our graduated cylinder, and we're going to have 30 milliliters of acetic acid filled. We're going to go ahead and get an Erlenmeyer flask, and we're going to pour our acetic acid in there, and we're going to get some Thymol blue indicator, and we're going to put 5 drops, so 1, 2, 3, 4, 5. And we're going to go ahead and give that a mix, and we're going to want to go ahead and immediately open our stopcock, twist open our stopcock, and let our titration start. For every 1 milliliter of sodium hydroxide that is added, we're going to want to record the pH of that. And as well, the Thymol blue indicator will let us know when the equivalence point is hit for our titration, because it will turn a blue color like this, and that's when we know our end point has reached, our equivalence point has been reached. So when this happens, our titration has finished. However, we're gonna let 2 more milliliters of our sodium hydroxide run through, be added, just so for data points, so we can later go ahead and graph that. Now, for the calculations that we're going to obtain from this titration, we have, first starting with molarity, we have molar mass of acetic acid, pKa, and we have Ka. Now, for molarity, we're going to want to convert our milliliters to liters, and that's milliliters of the acetic acid, the volume of acetic acid, and the volume of this sodium hydroxide. And we see here how we do that. And over here, for step 2, we're going to go ahead and we're going to want to get the converted liters, and we're going to want to turn our liters to moles for sodium hydroxide, because over here we see that we take those moles of sodium hydroxide and we pretty much just divide it by our volume of acetic acid, which is 0.03 liters, as we saw up here how we got that. And over here is just the ratio of moles, and it's just 1 to 1, so we can pretty much ignore that and just say that to calculate the molarity we just need to divide moles of sodium hydroxide by the volume of acetic acid, and we get our molarity, which is 0.7 moles. For molar mass, we get our mass of acetic acid, which is 9 grams, and we're going to get our molarity, which we just saw how we calculated, and we're going to divide that. So 9 grams, but pretty much of mass of acetic acid divided by 0.7 molarity. And these are just the 1 to 1, so that's pretty much what we're doing, just division right there. And we see that the molar mass is 128.57 grams over moles of acetic acid. Now for pKa, we're going to introduce a new equation, which is the Henderson-Hasselbalch equation, and that basically states that our pH is equal to our pKa plus log times our moles of base divided by our moles of acetic or acid, and pKa is equal to pH at the half titration point. So this basically means that if our pH is 4.72, that means our pKa is also 4.72. And the reason that even though we have this whole log calculations, it doesn't really matter because our moles are 1 to 1. The log of 1 is 0, so that just means that 4.72 equals 4.72 pKa, which is our pH, which is that's just pKa. And for Ka, basically pKa and Ka are inversely proportional. Therefore, we just need to do 10 to the power of negative 4.72. And then we have our Ka, which is when we just round in scientific notation, that's just 2.10 to the negative 5th power.